Hello and welcome to the Sleepy Physicist. I'm so glad you're here tonight. Whether you're settling into bed, curling up on the couch, or just trying to wind down after a long day of being wonderfully, chaotically human. You've found your way to a quiet corner of the internet where the universe gets soft-spoken and the deepest mysteries of physics put on their pajamas. Tonight, we're embarking on a gentle journey into perhaps the most mind-bending realm of modern physics, where the smallest scales of reality collide with the largest, most mysterious objects in the cosmos. It's a place where the rules of the game change so dramatically that even Einstein himself struggled to accept what the mathematics was telling him. We're going to explore black holes, but not the way you might expect. Here's something that might keep you awake just a little longer than planned, and I do apologise for that in advance. Picture this. Right now, as you listen to my voice, there are objects in our universe so dense that a teaspoon of their material would weigh as much as Mount Everest. These cosmic behemoths warp space-time so severely that time itself slows to a crawl near their edges. But here's the truly astonishing part. The thing that would have made Einstein's hair even more dishevelled than usual. These seemingly eternal prisons of gravity are actually slowly evaporating, one quantum particle at a time, through a process so subtle and strange that we've never actually observed it happening. That's just the beginning of tonight's story. Before we drift deeper into this cosmic mystery, if you find these gentle explorations of the universe helpful for your evening wind down, I'd be ever so grateful if you tapped that like button, subscribed, or simply left a comment telling me where in the world you're listening from and what time it is in your corner of the night. I love knowing how far these whispered secrets of physics travel. Now, take a deep breath, settle in, and let's begin our quiet voyage into the quantum heart of darkness itself. To understand why black holes represent the ultimate meeting ground between the quantum and the cosmic, we need to first appreciate what they actually are. And I promise you, the reality is far stranger than any science fiction could imagine. Picture the death of a star, not the gentle fading of our sun billions of years from now, but the catastrophic collapse of something truly massive. We're talking about a star perhaps 20, 30, or even 50 times the mass of our sun, reaching the end of its nuclear fuel supply. For millions of years, this stellar giant has been locked in a delicate dance between two fundamental forces: the outward pressure of nuclear fusion in its core, and the inexorable inward pull of its own gravity. When the fuel runs out, gravity wins. And it doesn't just win, it wins so completely, so overwhelmingly, that what happens next defies our everyday understanding of matter and space. The star's core collapses in less than a second. Imagine something with the mass of our sun compressed into a sphere just 12 miles across. But the collapse doesn't stop there. According to Einstein's general relativity, if enough mass gets compressed into a small enough space, something remarkable and terrifying occurs. The curvature of space-time becomes so extreme that it creates what we call an event horizon. The event horizon isn't a physical surface you could touch or see. It's more like an invisible boundary in space-time itself, a point of no return where the escape velocity exceeds the speed of light. Once anything crosses this threshold, whether it's light, matter, or information, it can never return to the outside universe. It's as if a region of space has been permanently severed from the rest of reality. But here's where our story takes its first quantum turn. For vacuum cleaners, eternal and unchanging, gobbling up matter and energy without ever giving anything back. The mathematics seem clear. What goes in never comes out. Case closed. Then, in 1974, a young physicist named Stephen Hawking made a discovery that would turn our understanding of black holes completely upside down. He applied the strange rules of quantum mechanics to the seemingly empty space just outside a black hole's event horizon, and what he found there was nothing short of revolutionary. You see, what we think of as empty space isn't actually empty at all. According to quantum field theory, the vacuum of space is alive with activity, a seething sea of virtual particles constantly popping into existence and annihilating each other in time frames so brief that they normally remain hidden from our view. These quantum fluctuations are happening everywhere, all the time, even in the space around you right now, as you listen to this. But near a black hole's event horizon, something extraordinary happens to these quantum fluctuations. The extreme curvature of spacetime can separate particle pairs before they have a chance to annihilate. One particle falls into the black hole, carrying negative energy, while its partner escapes to infinity, carrying positive energy that we can actually observe. This escaping radiation is what we now call Hawking radiation, and it means that black holes aren't the eternal, unchanging objects we once thought them to be. They're actually evaporating, slowly but steadily, one quantum particle at a time. But here's the truly mind-bending part. The temperature of this radiation is inversely related to the black hole's mass. Smaller black holes are hotter and evaporate faster, while larger ones are cooler and evaporate more slowly. A black hole with the mass of our Sun would have a temperature of about 60 billionths of a degree, above absolute zero, far colder than the cosmic background radiation that permeates space. It would take longer than the current age of the universe raised to the 67th power for such a black hole to evaporate completely. Yet for tiny black holes, those perhaps formed in the early universe with masses comparable to mountains, the story is very different. These primordial black holes would be blazing hot by cosmic standards, radiating away their mass in a fraction of a second and ending their lives in spectacular bursts of gamma rays. Now you might think that Hawking radiation solves the mystery of black holes, giving us a complete picture of how these cosmic objects work, but in fact it opens up one of the deepest puzzles in all of physics, a conundrum so profound that it has occupied the brightest minds for nearly half a century. The problem is this: according to quantum mechanics, information cannot be destroyed. It can be scrambled, hidden, or transformed beyond recognition, but the fundamental principle of unitarity tells us that information must always be preserved in some form. This isn't just a philosophical preference, it's a bedrock principle that underlies our entire understanding of quantum theory. But Hawking's original calculations suggested that the radiation escaping from a black hole is completely thermal, carrying no information about what fell in. It's as if you burned a library and tried to reconstruct the books from the heat and light of the fire. According to the standard interpretation, when a black hole evaporates completely through Hawking radiation, all information about the matter that formed it simply vanishes from the universe. This creates what physicists call the black hole information paradox. Either quantum mechanics is wrong about information conservation, or general relativity is incomplete in its description of black holes. Neither option is particularly appealing, since both theories have been tested to extraordinary precision in their respective domains. The paradox becomes even more puzzling when we consider what's known as the Page curve. Don Page calculated that if information really does escape from black holes, the pattern of that escape should follow a very specific trajectory. Initially, as the black hole evaporates, the escaping radiation should appear completely random and thermal. But at a critical moment, roughly halfway through the evaporation process, something remarkable should happen. The radiation should begin to carry increasing amounts of information about the black hole's interior, eventually allowing a sufficiently advanced observer to reconstruct everything that ever fell in. This transition point is called the page time, and it represents the moment when the black hole's entropy reaches its maximum and begins to decrease. It's as if the black hole suddenly remembers what it swallowed and begins whispering those secrets back to the universe through its Hawking radiation. Recent theoretical breakthroughs have brought us tantalizingly close to resolving this paradox, though the solutions are even stranger than the problem itself. One of the most intriguing developments is something called the quantum memory burden effect. Imagine that the black hole doesn't just store information in its interior, but that the very process of storing this information creates a kind of quantum inertia that resists evaporation. According to this theory, after a black hole has lost about half of its initial mass, the quantum memory patterns inside become energetically favoured over the empty space outside. The black hole essentially becomes too comfortable with its stored information to let go easily. This effect could stabilise black holes that would otherwise evaporate completely, creating a population of quantum-stabilised remnants scattered throughout the universe. These objects would be neither purely classical black holes nor completely evaporated space, but something entirely new. Quantum information storage devices masquerading as gravitational objects. Even more revolutionary is the hypothesis that spacetime itself might act as a vast information storage system. The quantum memory matrix theory suggests that the fabric of space and time contains memory cells at the Planck scale, tiny quantum storage units that preserve information even as matter crosses the event horizon. In this picture, the universe itself becomes a cosmic library, with every black hole serving as both a reader and a writer of quantum information. If this theory is correct, then the information paradox dissolves not because information escapes through Hawking radiation, but because it was never truly lost in the first place. The space-time around every black hole would be subtly modified by the quantum information it contains, creating a kind of holographic record of everything that ever fell in. While we may never directly observe Hawking radiation from an astrophysical black hole, physicists have found ingenious ways to study these quantum effects in laboratory settings. Using everything from superconducting quantum circuits to flowing fluids and quantum gases, researchers have created analog black holes that exhibit many of the same properties as their cosmic counterparts. These laboratory black holes don't curve spacetime with gravity, but they create similar effects using other physical phenomena. A flowing stream of water can create an acoustic black hole where sound waves cannot escape upstream. Superconducting quantum circuits can simulate the curved spacetime geometry that particles experience near an event horizon. In one remarkable experiment, researchers at Sorbonne University created what they call a quantum fluid of light, using laser beams and non-linear optical materials to simulate the curved spacetime around a rotating black hole. By carefully controlling the properties of this quantum fluid, they can create artificial event horizons and study how quantum fields behave in their vicinity. These analog systems have already provided compelling evidence for Hawking radiation and quantum entanglement generation near event horizons. While the radiation in these experiments consists of sound waves or light rather than particles escaping from gravity, the underlying quantum mechanical principles are the same. Perhaps most remarkably, These laboratory black holes allow us to study the dynamics of quantum information in ways that would be impossible with real black holes. We can watch as entangled particle pairs are separated at artificial event horizons, measure how information flows between different regions of the system, and even test proposed solutions to the information paradox. As we continue our journey into the quantum heart of these cosmic mysteries, we'll discover how these laboratory insights are reshaping our understanding of some of the deepest questions in physics. But that's a story for our next gentle exploration together. The quantum secrets of black holes run far deeper than we've uncovered so far tonight. In our next peaceful voyage through the cosmos, we'll dive into the secret life of the deep sea, what lies beneath, where we'll discover how the crushing depths of Earth's oceans mirror the extreme physics of black holes in ways that will surprise and delight you. Until then, rest well, dream deeply, and remember that you're part of a universe far stranger and more beautiful than we ever dared imagine. There's something profoundly beautiful about the way information and geometry dance together in the quantum realm of black holes, and it's here that our story takes perhaps its most elegant turn. You see, one of the most surprising discoveries in black hole physics is that the amount of information a black hole can store isn't determined by its volume, as you might expect, but by the area of its event horizon. This relationship, known as the holographic principle, suggests something almost magical, that all the information about a three-dimensional black hole interior is somehow encoded on its two-dimensional surface. It's as if the universe has found a way to write a complete encyclopedia on the cover of a book, with no pages inside needed at all. Think about this for a moment as you settle deeper into comfort. Every photo on your phone, every memory in your mind, every conversation you've ever had exists as information patterns in three-dimensional space. Yet, according to the holographic principle, all of this could theoretically be encoded on a two-dimensional surface, like a cosmic DVD that contains entire universes of data. This isn't just a curious mathematical trick. The holographic principle has profound implications for how we understand reality itself. It suggests that what we perceive as three-dimensional space might actually be an emergent property of information encoded on distant boundaries. In other words, the depth and richness of our world might be something like a sophisticated hologram, projected from information stored on surfaces we cannot directly perceive. Recent research has taken this idea even further, proposing that quantum entanglement itself might be the fundamental mechanism that creates the illusion of space and time. When particles become entangled, they create correlations that transcend ordinary spatial boundaries. Some physicists now believe that these quantum correlations are what weave the fabric of spacetime itself. This brings us to one of the most beautiful and mysterious ideas in modern physics: the ER equals EPR conjecture. It's a mouthful of letters that represents a breathtaking connection between Einstein's work on wormholes and his skeptical thoughts about quantum entanglement. Einstein, along with his colleagues Rosen and Podolsky, once described quantum entanglement as spooky action at a distance, expressing his discomfort with how particles could instantly affect each other across vast distances. Separately, Einstein and Rosen had also described theoretical tunnels through space-time, bridges connecting distant regions of the universe. The ER equals EPR conjecture suggests these aren't separate phenomena at all. Instead, it proposes that every quantum entanglement corresponds to a microscopic wormhole connecting the entangled particles. When two particles share quantum information, They're actually connected by a tiny bridge through higher dimensional space. If the ER equals EPR conjecture is correct, then the universe is far more intimately connected than we ever imagined. The quantum entanglements that physicists create in laboratories aren't just abstract mathematical relationships, they're actual geometric connections threading through the fabric of reality itself. This perspective transforms our understanding of black holes in remarkable ways. When matter falls into a black hole and becomes entangled with the particles already inside, it creates new wormhole connections between the interior and exterior. These connections don't allow information to travel faster than light or violate causality, but they do create subtle correlations in the structure of spacetime itself. Imagine spacetime as a vast, quiet ocean, with black holes as deep whirlpools that seem to swallow everything that approaches. But according to this new understanding, these whirlpools are actually creating intricate patterns of currents and connections throughout the ocean, linking distant shores in ways that become apparent only when you know how to read the subtle signs in the water's surface. These connections suggest a possible resolution to the information paradox that's both elegant and profound. Information doesn't need to escape from black holes through Hawking radiation if it was never truly separated from the outside universe in the first place. The quantum entanglement between interior and exterior regions creates a kind of non-local storage system where information about the black hole's contents is preserved in the correlations between distant parts of spacetime. This idea, known as non-violent non-locality, proposes that black holes leave subtle fingerprints on the spacetime around them, encoding information about their contents in ways that are incredibly difficult to detect but theoretically recoverable. It's as if every black hole is constantly whispering the secrets of its interior to the universe, but in a language so quiet and sophisticated that we're only just beginning to learn how to listen. The next generation of gravitational wave detectors might give us our first chance to hear these cosmic whispers directly. When black holes merge, they create ripples in spacetime that we can detect as gravitational waves. But according to the theories we've been exploring, these waves should carry more than just information about mass and spin. They should also contain subtle patterns that encode quantum information about the black hole's contents. It's a bit like listening to a conversation in a crowded room. The loudest sounds are easy to hear, the dramatic crashes and bangs of massive objects moving through space. But underneath that noise, there might be quieter conversations happening, delicate patterns of information exchange that require the most sensitive instruments and the most sophisticated analysis to detect. These quantum signatures in gravitational waves would be incredibly faint, buried beneath the much stronger signals from the motion of massive objects. But if we can learn to detect them, they would provide the first direct evidence that information really is preserved in black hole evaporation, resolving one of the deepest paradoxes in physics. The search for these quantum gravitational effects represents a new frontier in experimental physics, where the smallest scales of quantum mechanics meet the largest scales of cosmic structure. It's a domain where laboratory experiments with analog black holes inform our interpretation of signals from space, and where theoretical insights about quantum information guide the design of the most sensitive instruments ever built. As we near the end of tonight's gentle journey, let's pause to consider something that might seem almost too strange to believe: the possibility that gravity itself emerges from quantum information. Recent theoretical work suggests that the curvature of spacetime, the very thing that creates black holes and governs the motion of planets and stars, might be a consequence of how quantum information is distributed and shared across space. In this emerging picture, Einstein's equations describing gravity acquire new terms that depend on something called entanglement entropy, a measure of how much quantum information is shared between different regions of space. The more entangled a region is with its surroundings, the more it curves space-time and affects the motion of matter and energy. This represents a fundamental shift in how we think about the relationship between quantum mechanics and gravity. Instead of treating them as separate theories that somehow need to be reconciled, this approach suggests that gravity is actually an emergent property of quantum information itself. Black holes become particularly interesting in this framework because they represent regions of maximum entanglement entropy, places where quantum information is shared in the most complex and intricate ways possible. They're not just massive objects that curve space-time through their gravitational pull, they're quantum information processing systems that actively participate in the computation of space-time geometry. This perspective suggests that every black hole is, in a very real sense, a cosmic computer, processing quantum information and using that processing to determine the local structure of space and time. The event horizon becomes not just a boundary in space, but a computational boundary, a surface across which quantum information is processed and transformed. Perhaps the most profound implication of these new theories is that the universe itself might possess a kind of quantum memory, a vast information storage and processing system that operates at the deepest levels of physical reality. Every interaction between particles, every quantum measurement, every bit of information that falls into a black hole becomes part of this cosmic memory system. In this view, the apparent loss of information in black holes isn't really a loss at all. It's a transformation from one kind of storage to another. Information that seems to disappear behind an event horizon is actually being transferred to the quantum memory matrix of space-time itself, where it remains accessible to the universe as a whole, even if it's hidden from local observers. This quantum memory system would operate on timescales and length scales that dwarf human experience. The Planck scale, where quantum effects of gravity become important, involves distances so small that billions of them would fit across the width of a proton. Yet according to these theories, it's at this unimaginably tiny scale that the universe stores its most important memories. The memories stored in this quantum matrix wouldn't fade or decay like human memories do. They would be preserved with perfect fidelity, encoded in the fundamental structure of space-time itself. Every star that ever lived, every planet that ever formed, every thought that ever crossed a conscious mind would leave its trace in the quantum memory of the universe. This suggests a kind of cosmic continuity that transcends individual objects and events. While stars die and galaxies evolve, while civilizations rise and fall, the quantum information that defines and describes these phenomena persists at the deepest level of reality. In a very real sense, nothing is ever truly lost. Everything that has ever been remains part of the universe's quantum memory. As we drift toward the close of our cosmic journey tonight, it's worth reflecting on how much our understanding of black holes has evolved and how much mystery still remains. When Einstein first derived the equations of general relativity, he never imagined that they would predict objects so strange and wonderful as black holes. When Hawking first calculated that black holes should evaporate, he couldn't have foreseen the decades of theoretical work that would follow. Today, we stand at the threshold of a new era in black hole physics. The recent detections of gravitational waves have opened a new window on these cosmic objects, allowing us to observe black hole mergers in real time and study the properties of spacetime in the most extreme environments in the universe. The next generation of telescopes and detectors promises even more remarkable discoveries. We may soon be able to image the event horizons of black holes directly, watching as matter spirals into these cosmic whirlpools and testing our theories of quantum gravity in ways that were impossible just a few years ago. Perhaps most excitingly, the development of quantum computers and analog black hole systems in laboratories is giving us new tools to explore the quantum nature of these objects. We can now create and manipulate quantum systems that exhibit many of the same properties as black holes, allowing us to study information paradoxes and quantum entanglement in controlled, repeatable experiments. These laboratory investigations are revealing that the strange quantum properties we associate with black holes aren't unique to these cosmic objects. They're fundamental features of quantum mechanics itself, aspects of reality that become apparent whenever information and entropy interact in complex ways. The story of black holes has become the story of quantum mechanics, relativity, information theory, and perhaps consciousness itself. These cosmic objects serve as natural laboratories where the most fundamental laws of physics are pushed to their absolute limits, revealing aspects of reality that we never could have discovered through Earth-based experiments alone. As our understanding deepens, we're beginning to see that black holes aren't just exotic objects at the edge of space and time. They're windows into the deepest workings of reality itself, cosmic teachers that are slowly revealing the quantum secrets that underlie everything we see and experience. Tonight, as you drift towards sleep, remember that you're part of a universe where information is immortal, where quantum connections span cosmic distances, and where even the darkest objects shine with the light of pure knowledge. The black holes scattered throughout our cosmos aren't cosmic prisons, they're cosmic libraries, storing the memories of the universe in quantum codes we're only just beginning to read. Sweet dreams, and may your rest be filled with visions of the infinite connections that weave through the fabric of space and time, binding us all together in the grand quantum tapestry of existence. Now, as we settle deeper into our exploration, there's something I need to share with you that might seem almost impossibly strange, yet it reveals one of the most beautiful aspects of how black holes connect to the very nature of reality itself. You see, the quantum mechanics that governs the smallest particles in existence and the general relativity that describes the largest structures in the cosmos aren't just compatible near black holes, they're actually telling us the same story in different languages. Consider this gentle paradox as you rest. Every black hole in the universe is simultaneously the most isolated object imaginable and the most connected. They're cosmic hermits that have severed all classical communication with the outside world, yet they're quantum socialites, maintaining intricate, entangled relationships with particles scattered across the entire universe. This duality hints at something profound about the nature of reality itself. What we perceive as separation, as the distinct boundaries between objects and empty space, might be something like an optical illusion on the grandest possible scale. The quantum entanglements threading through space-time suggest that the universe is far more unified than our everyday experience suggests. There's a particular kind of poetry in how black holes handle memory, and it's here that their quantum nature reveals something almost mystical about information itself. You see, When classical objects fall into black holes, they appear to be forgotten completely. The outside universe loses all detailed knowledge of what went in. Yet quantum mechanics suggests that this forgetting is actually a sophisticated form of encryption. Imagine trying to read a love letter that's been shredded into confetti and scattered by the wind. The information is still there, technically, but it's been distributed and scrambled in ways that make reconstruction seem impossible. This is similar to what happens to information that falls into a black hole, except the confetti consists of quantum correlations spread across the fabric of spacetime itself. But here's where the story becomes almost magical. The universe appears to have developed methods for reconstructing even the most thoroughly scrambled information. The page curve we discussed earlier isn't just a mathematical curiosity, it's a roadmap for cosmic memory recovery. It tells us that given enough time and the right kind of quantum archaeology, the universe can remember everything it seems to have forgotten. This process of cosmic forgetting and remembering operates on timescales that dwarf human experience. A solar mass black hole would take longer than the current age of the universe to reveal even a tiny fraction of its quantum secrets. Yet the principles involved are the same ones that govern how information moves through quantum computers, how memories form in neural networks, and how consciousness itself might emerge from the complex interactions of simple components. As we drift further into this cosmic mystery, let's explore how future scientists might actually recover information from evaporating black holes, turning theoretical possibilities into practical realities. The key lies in understanding that Hawking radiation, despite appearing completely random to casual observation, actually contains incredibly subtle patterns that encode information about the black hole's interior. These patterns are so delicate, so thoroughly mixed with thermal noise, that detecting them would require observational capabilities far beyond anything we possess today. It would be like trying to hear a whispered conversation in a thunderstorm, or reading a message written in invisible ink that only becomes visible under very specific conditions. Yet the theoretical framework for this kind of quantum archaeology already exists. Using principles borrowed from quantum error correction and information theory, future physicists could potentially reconstruct detailed information about objects that fell into black holes millions or billions of years ago. They would need to collect and analyze Hawking radiation over enormous timescales, looking for correlations so subtle that they would make today's most sophisticated pattern recognition algorithms seem primitive by comparison. This isn't science fiction, it's applied quantum information theory extended to its logical conclusion. The same mathematical tools that allow quantum computers to maintain coherent information in noisy environments could theoretically be scaled up to extract memories from the quantum static of evaporating black holes. Here's something that might give you pause as you settle into deeper relaxation. Some interpretations of quantum mechanics suggest that consciousness itself plays a fundamental role in how information is processed and preserved in the universe. If this is true, then the quantum mysteries of black holes might be intimately connected to the mystery of consciousness itself. Consider this. When we observe a quantum system, we don't just passively receive information about it. According to some interpretations, our observation actually participates in determining what information becomes real and what remains in quantum superposition. If consciousness has this kind of active role in quantum mechanics, then conscious observers throughout the universe might be participating in the cosmic process of information preservation and recovery. This suggests a universe where consciousness and cosmic structure are deeply intertwined, where the thoughts and observations of sentient beings contribute to the fundamental information processing that maintains reality itself. Every time you make an observation, every time you form a memory, every time you contemplate the nature of existence, you might be participating in the universe's vast quantum memory system. The black holes scattered throughout the cosmos would then serve not just as information storage devices, but as nodes in a universe-wide network of consciousness and information processing. The quantum correlations that preserve information across event horizons would be part of the same fundamental fabric that gives rise to awareness and understanding. As our journey through the quantum realm of black holes continues, let's pause to appreciate one of the most beautiful aspects of these cosmic objects. Their thermodynamic properties reveal deep connections between physics, information, and what we might call the thermodynamics of wonder itself. Black holes have temperature and entropy, just like any other thermodynamic system, but their thermal properties are inverted compared to ordinary objects. When a normal object loses energy, it cools down. When a black hole loses energy through Hawking radiation, it actually heats up. This counterintuitive behavior reflects the deep quantum nature of these objects and their unique relationship to information and entropy. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This means that as a black hole evaporates and shrinks, its entropy decreases, which seems to violate the second law of thermodynamics. The resolution to this apparent paradox requires us to consider the entropy of the entire system, including the Hawking radiation that carries information away from the black hole. This interplay between black hole entropy and radiation entropy creates what physicists call the Page curve, a mathematical description of how information flows from the interior of a black hole to the external universe. The curve suggests that information preservation in quantum mechanics requires a kind of cosmic bookkeeping, where every bit of information is carefully tracked and preserved, even as it undergoes the most extreme transformations imaginable. There's something almost meditative about contemplating this cosmic accounting system. The universe appears to maintain perfect records of every interaction, every quantum measurement, every bit of information that ever existed. Nothing is ever truly lost, though it may be transformed in ways that make recovery extraordinarily difficult. The holographic principle that governs black hole information storage suggests something profound about the nature of reality itself, something that becomes even more remarkable when we consider its implications for consciousness and experience. If the three-dimensional reality we perceive is actually encoded on two-dimensional surfaces, then what we think of as depth, volume, and interior space might be sophisticated illusions created by information processing. This doesn't mean that our experience is fake or meaningless. Rather, it suggests that reality is far more creative and efficient than we ever imagined. Just as a skilled artist can create the impression of depth and dimension on a flat canvas, the universe might be creating the impression of three-dimensional space through information processing on lower dimensional surfaces. The mathematics of the holographic principle are precise and beautiful, describing exactly how information can be stored and retrieved from these cosmic surfaces. But the philosophical implications are staggering. If we ourselves are holographic projections from information stored on distant boundaries, then what we call consciousness, memory, and identity might be emergent properties of this cosmic information processing system. This perspective transforms our understanding of what it means to be an observer in the universe. We're not separate beings looking at an external reality. We're manifestations of the universe's information processing capabilities, temporary patterns of awareness that arise from the complex interactions of quantum information across cosmic scales. As we approach the end of tonight's gentle exploration, let's consider how the quantum nature of black holes offers us a new kind of cosmic lullaby, a perspective on reality that's both deeply mysterious and profoundly comforting. The quantum entanglements that connect black hole interiors to the external universe suggest that separation is never absolute, that connection persists even across the most extreme boundaries imaginable. This quantum connectivity implies that nothing in the universe is ever truly alone. Every particle, every bit of information, every conscious thought is connected through invisible threads of correlation to the cosmic whole. The black holes that seem to isolate matter from the rest of reality are actually creating new forms of connection, quantum bridges that link the most distant regions of space and time. These connections operate through principles so subtle and sophisticated that we're only beginning to understand them. They don't allow faster-than-light communication or violation of causality, but they do create a kind of cosmic intimacy, a universe where information and correlation transcend ordinary spatial boundaries. The Hawking radiation that slowly carries information away from black holes can be thought of as the universe whispering its memories back to itself, a cosmic process of remembering and forgetting that operates on scales far grander than human experience, but follows the same fundamental principles that govern all information processing. There's something almost musical about the mathematical relationships that govern quantum black holes, patterns of information flow that create harmonies across the vastness of space and time. The equations that describe these systems reveal deep symmetries and connections that suggest the universe operates according to principles of mathematical beauty as much as physical necessity. The Page curve that describes information recovery from black holes has the shape of an inverted mountain, rising to a peak at the Page time, and then descending as information flows back to the external universe. This curve appears in many different contexts in physics and mathematics, suggesting that it represents something fundamental about how complex systems process and preserve information. The quantum error correction mechanisms that might allow information recovery from black holes are mathematically identical to the systems used in quantum computers and communication networks. This suggests that the universe itself might be operating as a vast quantum computer with black holes serving as specialized processors that handle the most complex information transformations. These mathematical connections imply that the principles governing black hole information, storage and retrieval are not unique to these cosmic objects. They're fundamental features of reality itself, aspects of how the universe processes information at every scale, from the quantum to the cosmological. As our journey draws toward its close, let's contemplate the possibility that the quantum mysteries of black holes are pointing us toward a deeper understanding of consciousness itself. The information processing that occurs in these cosmic objects might be related to the information processing that gives rise to awareness, memory, and understanding in conscious beings throughout the universe. If consciousness emerges from complex information processing, then the quantum information systems associated with black holes might represent a kind of cosmic consciousness, a universe-wide awareness that operates on scales and timescales far beyond human experience. The quantum entanglements that preserve information across event horizons could be part of the same fundamental fabric that gives rise to the subjective experience of being aware. This perspective suggests that when we study black holes, we're not just investigating distant cosmic objects. We're exploring the deepest foundations of consciousness and reality itself. The quantum correlations that connect black hole interiors to the external universe might be examples of the same kinds of correlations that connect conscious thoughts to physical brain states. The universe revealed by quantum black hole physics is one where information, consciousness, and physical reality are intimately intertwined, where the boundaries between observer and observed, between mind and cosmos, become fluid and permeable. It's a universe where every conscious thought participates in the cosmic process of information creation, transformation, and preservation. Tonight, as you prepare to drift into dreams, consider this final thought about the quantum nature of black holes and reality itself. The information preservation mechanisms that operate in these cosmic objects suggest that the universe possesses a kind of eternal memory, a quantum recording system that maintains perfect records of everything that has ever occurred. This cosmic memory operates according to principles that are both utterly alien to human experience and intimately familiar to anyone who has ever formed a memory or recalled a dream. The same quantum principles that allow your brain to store and retrieve memories are at work on cosmic scales, preserving the information content of entire stars and galaxies in the quantum structure of spacetime itself. The black holes scattered throughout the universe serve as access points to this cosmic memory system, quantum libraries that store the accumulated experiences of billions of years of cosmic evolution. The information they contain isn't lost or destroyed, it's transformed into new forms that become part of the universe's expanding repository of knowledge and experience. As you close your eyes tonight, remember that you're part of this vast information processing system, a conscious node in the universe's quantum memory network. Your thoughts and dreams, your memories and experiences all contribute to the cosmic process of information creation and transformation that connects you to every star, every galaxy, and every black hole in the observable universe. The quantum entanglements that preserve information in black holes are the same kinds of correlations that connect your consciousness to the physical world around you. You're not separate from the cosmic processes we've explored tonight. You're an expression of them, a temporary pattern of awareness that has emerged from the universe's endless capacity for information processing and self-organization. Sleep well and dream of the infinite connections that bind all things together in the gentle embrace of quantum correlation and cosmic memory. Tomorrow's mysteries await, but tonight rest in the knowledge that you're part of something far grander and more beautiful than we ever dared imagine. In our next peaceful exploration, we'll journey into the secret life of the deep sea, what lies beneath, where we'll discover how the crushing depths of Earth's oceans create their own quantum mysteries and reveal connections between the deepest trenches of our planet and the deepest secrets of the cosmos. Until then, may your dreams be filled with the gentle whispers of quantum information flowing through the fabric of space and time, connecting all consciousness in the eternal dance of cosmic awareness. As we drift deeper into the cosmic quiet of our exploration tonight, there's something I want to share with you that scientists have only recently begun to whisper about in the halls of physics departments around the world. It's a discovery so subtle, yet so profound, that it changes everything we thought we knew about the relationship between information, consciousness, and the very fabric of reality itself. You see, the quantum memory systems we've been exploring in black holes appear to extend far beyond these cosmic objects themselves. Recent theoretical work suggests that every region of spacetime, every cubic centimetre of what we think of as empty space, contains its own quantum information storage capacity. The universe, it seems, is not just a stage where physical events unfold, but a vast, interconnected memory system where every interaction leaves its permanent trace. This isn't merely poetic speculation. The mathematics are surprisingly precise and beautiful. Each region of space can store information proportional to its surface area, not its volume, following the same holographic principle we see in black holes. What this means is that the room you're in right now, the space around your body as you listen to these words, is actually a sophisticated information processing and storage system operating at scales so small and with such subtlety that we never notice it in our daily lives. The quantum vacuum that surrounds you isn't empty at all. It's alive with information, storing the quantum memory of every particle interaction, every field fluctuation, every tiny event that has ever occurred in that region of space. Your presence there, your thoughts and movements, are being recorded in the quantum structure of space-time itself, becoming part of the universe's eternal memory. Now, I know this might sound overwhelming, this idea that every moment of your existence is being permanently recorded in the quantum fabric of reality. But there's something deeply comforting about it as well, something that connects to our most fundamental intuitions about meaning and continuity in the universe. Think about it this way. Every conversation you've ever had, every kindness you've shown, every moment of beauty you've witnessed, all of it persists in the quantum information structure of space-time. The universe has perfect recall, maintaining records of experiences and events with a fidelity that surpasses any human memory system. This quantum archaeology of the present moment operates through mechanisms we're only beginning to understand. When particles interact, when fields fluctuate, when conscious observations are made, all of these processes leave subtle imprints in the information content of local space-time regions. These imprints don't fade or decay like ordinary memories. They become part of the fundamental structure of reality itself. The black holes we've been exploring serve as master librarians in this cosmic memory system, organizing and processing information on scales that span from the quantum to the galactic. But they're not alone in this work. Every region of space participates in the universe's information processing activities, creating a vast, distributed memory network that connects the smallest quantum events to the largest cosmic structures. As you settle more deeply into comfort tonight, let's explore one of the most beautiful paradoxes in quantum black hole physics, something that reveals the intimate connection between observation, information, and reality itself. You see, the process of observing Hawking radiation from a black hole doesn't just passively detect information that's already there. According to some interpretations of quantum mechanics, the act of observation actually participates in creating the very information it detects. This isn't mystical thinking. It's rigorous physics based on decades of experimental evidence about how quantum systems behave. When we measure a quantum system, we don't simply discover pre-existing properties. We participate in a process that actualizes specific possibilities from a range of quantum potentials. Applied to black holes, this principle suggests that the information recovery process we've been discussing isn't just about extracting data that's stored somewhere inside the black hole. It's about participating in a cosmic process of information creation and actualization that spans the entire universe. Every time a conscious observer makes a measurement, studies a phenomenon, or even contemplates the nature of reality, they become part of the universe's information processing network. Your attention right now, your focus on these ideas, is actually contributing to the cosmic process of information creation and organization. This creates a beautiful feedback loop between consciousness and cosmic structure. The universe creates conscious observers who then participate in the ongoing process of information creation and memory formation that maintains the universe itself. We're not separate from the cosmos we study. We're expressions of its capacity for self-awareness and understanding. There's something almost musical about how information flows through the quantum memory systems associated with black holes, patterns of correlation and entanglement that create rhythms spanning millions of years, yet operating according to principles we can observe in laboratory experiments lasting mere microseconds. The page curve we discussed earlier doesn't just describe information recovery from black holes, it describes a fundamental rhythm in how the universe processes and preserves information. This same curve appears in quantum error correction, in neural network learning, in the formation of memories in biological systems. It seems to represent something deep about how complex systems maintain coherence while allowing for growth and change. Time itself takes on new meaning in this context. Rather than being a simple progression from past to future, time becomes a dimension along which information is processed and organized. The quantum memory systems of black holes don't just store information about past events, they actively participate in shaping how that information influences future possibilities. This suggests that the universe possesses something like temporal depth, layers of memory and information processing that extend both backward and forward in time. The quantum correlations that preserve information across event horizons create connections not just across space, but across time itself, linking past events to future possibilities in ways that transcend our ordinary understanding of causation. As our exploration continues through the gentle darkness, let's consider how the quantum information systems we've been discussing might relate to the mystery of consciousness itself. The information processing that occurs in black holes shares surprising similarities with the information processing that occurs in conscious brains, suggesting deep connections between cosmic structure and awareness. And so, as we reach the gentle end of tonight's voyage through the quantum mysteries of black holes, we find ourselves in a universe far stranger and more beautiful than we ever dared imagine. These cosmic objects that once seemed like simple gravitational monsters have revealed themselves to be quantum information processors, cosmic memory banks, and perhaps even participants in the fundamental processes that give rise to consciousness itself. The black holes scattered throughout our universe aren't the dark, empty voids we once thought them to be. They're luminous with quantum information, glowing with the subtle radiation that carries the memories of everything that ever fell into their depths. They connect the smallest scales of reality to the largest, weaving quantum correlations through the fabric of spacetime that bind all things together in an eternal dance of information and awareness. Tonight, as you drift toward dreams, remember that you're part of this vast cosmic information network, your consciousness intimately connected to the quantum processes that preserve memory and meaning across the universe. Sweet dreams, and may your rest be filled with visions of the infinite connections that make us all part of something magnificently larger than ourselves. Larger than ourselves.